So in my last video, my goal was to try to help you imagine what electromagnetic radiation might look like. And more importantly, I wanted you to understand that electromagnetic radiation isn't fundamentally any different from visible light. But if you actually look up the definition of light online, well, first off, you're going to get a whole bunch of different answers depending on the context. But I have a definition here from this article here, Measuring the Magnetism of Light, physicsapps.org. And here's the part that I'm trying to focus on. We have this definition of light here. Light is a wave of both electric and magnetic fields. You'll come across a bunch of different definitions that say something similar to that, but you'll also come across some definitions that talk about how light is both a wave and a particle. So we got waves, particles, and fields. And I wanted to make a video that gives context for those kinds of definitions. I wanted a video that explained what that actually means. So what does it mean for light to be a wave of electric and magnetic fields? What does it actually mean to be a wave? What does it actually mean to be a field? All right, so hopefully this video gives context to that. And so without further ado, let's just get this video underway. So I want to front load this video with a lot of what I'm going to call prerequisite information, because I want to make sure you never get put off by anything that I say in another future video. Yeah. So I'm going to be asking a lot of, I guess, seemingly mundane or ridiculous questions, because I just want to make sure that we're all on the same page from here on out. And the first of those questions that I want to ask you is, what is a wave? Now, if I ask you to picture a wave, you could probably have an easy time picturing something like maybe an ocean wave or a sound wave or something like that. But if I ask you to define what a wave is, how would you define it? Well, I don't know about you, but if someone were to ask me that sort of question, I'm just going to look it up on the internet. So that's what we're doing. Stand by, people. All right, so here we are on Wikipedia, and I've highlighted the very important part here, okay? Here is the definition that I want us all to focus on. A wave is a propagating dynamic disturbance or change from equilibrium of one or more quantities. Okay. Now, if none of that made any sense to you, we're going to break every part of that sentence down one piece at a time. So if we focus on this part, a change from equilibrium, so this is telling us that for us to have a wave, we need to have some sort of equilibrium or some kind of what I'm going to think of as like a default state. Now, Wikipedia actually has a definition for equilibrium here as well, so let's click on that. The condition of a system in which all competing influences are balanced. There you go. So for this, you could probably imagine something like a still body of water or just anything else like that where the forces are competing in balance, so nothing's moving very much or nothing significant is happening. When I like to picture, when I close my eyes, some sort of container floating in space, and it's full of some sort of mystery liquid, and this liquid is staying completely still. It's not moving at all. And I'm going to be using that analogy a little bit here in the future, so that's why I'm bringing it up now. So the word propagating in this sentence just means to move through something or to move out from some specific direction. So we know waves move, we know waves travel, so that makes sense. But the real key word here, I think, is quantities, because what this means is we need some sort of value to be changing for there to be a wave, either dynamically, as we can see here, or maybe cyclically. We need some sort of value to focus on that's constantly oscillating or changing or being disturbed in some sort of way. So this might sound obvious, but I think it's important to remember that a wave is not really an object so much as it is a process. It's not something that you generally hold, right? It's more akin to something like a fire or a waterfall or something. It's not A waterfall isn't an object so much as it is a process of water moving from a higher place to a lower place. So I think that's important to remind ourselves of before we move on any further. And real quick, I don't know the experience level of all the people who might be watching this thing. So after what I just said, I'm sure there might be at least some of you who are going to be going like, wait, what about wave particle duality? And I'm going to get to all that towards the end of the video, but I don't want to confuse anybody. So just shelve it for now and then we'll come back to it. For now, we're just focusing on the wave part. Anyways, I want to kind of clear up another language bug that we tend to use when it comes to electromagnetic radiation. It's not really a bug. It's not necessarily wrong, but a lot of textbooks and a lot of people will tell you that light will create an electromagnetic field it'll make an electric field and a magnetic field. And that's what light is. It's an electric field and a magnetic field traveling through space together. But I think that language that it is an electric field and a magnetic field moving through space, I think that can sometimes confuse people later on down the line. Especially if we abide by the more recent theories of physics, that it's more accurate to say that light is a disturbance in the electromagnetic field. So not just saying that it creates an electromagnetic field, but that it is a disturbance in the electromagnetic field. But what is the distinction? Well, to understand the distinction, we first need to make sure we understand what a field actually is, because I've seen a lot of science communicators kind of take that for granted. So a field is just a mathematical description. It's a portion of 2D, 3D, 4D, or whatever dimensional space you want to talk about, where every point has some sort of value associated with it, or maybe sometimes multiple values. And if you think about it, this is actually pretty mundane. Like, think about the immediate 3D space surrounding you. Think about every single point around you that you could reach within, say, 5 seconds. Well, you could give every single point immediately surrounding you a value, like how fast you can reach it, and you could call it something like the I can reach this in 5 seconds field, which admittedly is a terrible title, but you could do that. So a gravitational field is just this portion of 3D space where objects might feel some sort of gravitational force within that space. So a field is more of an abstraction than it is some sort of like real physical thing. So let's think back to our imaginary equilibrium for a second. We have a body of water in a container sitting perfectly still with no outside forces acting on it. All right, so we can imagine that this whole thing is a self-contained field, right? It's currently in equilibrium. And so remember earlier I highlighted the word quantities. So we're going to have to give every point in this field a value for it to actually be a field. So what values are we referring to? Well, the values that we're referring to is if we were to poof something into existence in this liquid, how much and in what direction would it move? Right? Those are the values we're looking at. How much and in what direction? All right, so I just wanted to interject real quick because I wanted to make a quick clarification. When I said what values are we focusing on, I mean, technically we could focus on any values that we wanted to, right? But I wanted to focus on values that were going to be relevant to what we're talking about next and that are pretty easy to understand, okay? So that's what I'm talking about when I chose this specific value. As of right now, because this thing is in equilibrium, a newly poofed in object would just float in there, not moving. Minus any sort of weirdness that comes with just like magically and instantaneously putting an object in the middle of something. I don't know. I've never been in that situation, but we're just gonna imagine that no extra weirdness happens. All right, so here's the kicker. Here's like the very important, may or may not blow your mind, we'll see. I want you to imagine that you are right now sitting in something that is very analogous to that body of water. You are currently sitting in the electromagnetic field. It is a big, expansive field in 3D space that entails our entire universe, and you are sitting smack dab in the middle of it. There's a whole lot of other fields too, also encompassing our universe, and they're all kind of layered on top of one another, but that's a whole separate topic or video, or that's not important when it comes to wireless communications. But that's the key difference here from what I was talking about from earlier. Light isn't just an electric field and a magnetic field traveling through space. It is a propagating disturbance in the electromagnetic field, the giant one that encompasses our whole universe. That's what we experience as light and electromagnetic radiation. So just to be clear, the textbooks that say that light is an electric field and a magnetic field, they're not wrong per se. I feel like the latter explanation is a little more modern and a little more consistent with what we know about waves and fields in general. And at least to me, it's a lot easier to imagine, which is really the key part. But it's also good to understand both descriptions so that when you come across one in any sort of textbook or anything like that, you're not confused. All right, so now what if we were to take that container of liquid that we've been imagining, and what if we were to just poof into existence in the center of this container a little ball that can vibrate when I hit a switch on a little remote. So when the ball poofs in, it's not vibrating. So for the most part, our liquid is still at equilibrium. Again, assuming no weirdness that comes with magical instantaneous teleportation. Then I hit the button and the ball starts vibrating back and forth ever so slightly. And as you might expect, you'd see waves in all directions originating from the little ball, creating a propagating disturbance in the liquid. Okay, so now let's replace this liquid with our universe's electromagnetic field and replace the little vibrating ball with something like a light bulb. And you'll see how light is a disturbance in the electromagnetic field, and to us that just happens to be perceived as light. And that's all pretty cool, but hang on a second, we're missing something. We said earlier that a field is a mathematical tool that describes a value or several values at every point in it. So with the electromagnetic field, what values are we referring to? What's the value that's actually changing? And this is the part that I'm actually going to keep the briefest in the video, because we could go down a rabbit hole, like a really big rabbit hole on electricity and magnetism and charged particles and so on and so on. But in a nutshell, it's very similar to our mystery goo from earlier. I said earlier that the values that we were tracking were how an object would move were it to poof into existence at any point in our liquid. Well, it's actually the same thing here, but the objects that we're referring to now are electrically charged particles. I am going to take one thing for granted here, and I am going to at least assume that you've heard of or have some sort of vague understanding of what an electron or a proton is. At least I hope you've at least heard of it before you clicked on this video. Electric and magnetic fields, they're constantly pushing and pulling charged particles around. So that potential for charged particles to get pushed or pulled around, that's what's constantly changing. That's what the disturbance is in this electromagnetic field. That's the value that's constantly changing. So like I said, electricity and magnetism could probably be its own video for how deep it can get. And that video would dive deeper on electric charge and the relationship between electricity and magnetism and understanding charged particles better. So hopefully that's enough context for you to imagine what's going on whenever we're talking about electromagnetic waves. I hope that now when you close your eyes, you can picture those electrically charged particles sort of being pushed back and forth, dancing in the ether. Okay, so I just wanted to clarify a couple things that I said throughout the video real quick. One of them being, I mentioned that there were a whole bunch of different fields, and that might have confused some of you out there, because if I said a field is just a mathematical description, technically we could choose whatever values we want. We could describe things in infinite ways. So what do I mean when I say there are more fields? I'm talking like there's a specific amount of them. So what I mean is we use fields to describe things. They're a description. And there are ways of describing our universe, like the way it works fundamentally. And there are only so many fields that fundamentally describe our universe. So that's what I mean by that. Like the gravitational field, for example, the electromagnetic field, for example, these are like fundamental fields that help us describe how our universe works. And so that's what I mean when the electromagnetic field is one of those fields. So I should have been a little more specific. I'm specifically referring to fields that are useful for describing how our universe works. Also, I want to make sure you understand that when we're talking about fields, or these kind of fields in particular, we're talking about fields that have the potential to move objects around. And obviously, well, maybe not obviously, you don't need the object to be there for the field to still exist, right? So the way I like to think about it is, if you had like a rubber duck in a bathtub, for example, and you started making waves in it, you would see that rubber duck moving up and down, right? But if you remove the rubber duck from the bathtub, you can still make waves in it, right? The rubber duck doesn't have to be there for you to be able to describe the waves in the bathtub, or to describe the bathtub as a field. And you could easily just put the rubber duck back in the bathtub to see it moving up and down like normal. So that's what I mean when I say that you don't need charged particles in electromagnetic fields for there to be a field in the first place, or waves in the first place. And that's the cool thing about light. Something we'll talk about later on, I think, is that it can move through space. It can move through a vacuum, and there doesn't have to be anything there for it to do that. The wave is always there, and so is the electromagnetic field. And there's one more thing that I want to address from earlier, and that was when I was hinting at this thing called wave-particle duality. And here's all I'm gonna say on it. Light is really complicated once you start to dive really deep into it. Like once you try to get into the minutia of what it is and how it works. And I'm not a physicist of any sort, so I'm not qualified to describe quantum mechanics to you, and I'm not really gonna try. I have used all this information in my day-to-day life. I used to have a job that it was relevant for me to know all this stuff. And I can tell you that understanding that light was both a particle and a wave at no point ever came up. It never would have been useful. It to this day wouldn't really be useful. For the purpose of wireless communications, you can just think of light as a wave. But what I will say is this: a photon is probably not what you think it is, and neither is a particle, even for that matter. Am I getting too deep into this? Maybe I am. So I already said that light is a process, and if you think about it, there's no reason that a wave should have a smallest unit, right? So for example, here, let me go to Desmos real quick. So if I'm here on Desmos and I put in a sine wave, right? This is a sine wave graphed on a number line, and we use these sine waves, we use these mathematical representations to describe all kinds of waves, but especially electromagnetic radiation. Now, if we zoom in, there is no reason why it doesn't look like a wave at this point. It just looks like a line, but we're still on the wave. You know that. We're still currently in the wave. We're still moving from one point to another point on this wave. And there's no reason that theoretically there should ever be a smallest point. There's no reason why we shouldn't be able to do this infinitely forever. Or at least, I mean, intuitively anyway. So we should be able to go getting smaller and smaller infinitely forever. But the truth is, in real life, light isn't actually like that. Even though it is a wave, for whatever reason, some reason, maybe no reason at all, when you get down to a small enough point, when you zoom in far enough on the wave that is light, there's going to come a point where the universe is just going to say, no, you can't have light any smaller than this. You must have at least this much wave for light to exist. And we call that minimum amount a photon. It's what we call a quanta of light. I should be mentioning here that most of this stuff is just like extra details. I don't think you need to remember any of this. This is just to try to make some of those weird feelings go away about like, wait, what about this and what about that? I don't want those feelings, but I also, I'm trying not to talk too much about stuff that's not really relevant. I am someone who really likes to think in analogies and in terms of stuff that I already understand. And while I like to learn about all this stuff as much as I can, I love watching videos on everything from radiation to chemistry to quantum mechanics. When it comes to the quantum mechanics part, I realize that there's going to be a point where you just can't do that anymore. You can't just think in terms of analogies, and you can't just think in terms of what you already know, because at some point it's just not going to, it can't relate to anything that you already know. It's just something else entirely its own. But my point here is that you don't really need to understand any of that to understand wireless communications or radios or microwaves or any of that. So for the purpose of this video and every video from here on out, we are just going to think of light as a wave. All right, so I made this part of the video its own video, and it still turned out to be a little longer than I expected it to be. But I really hope that it helped you, and I really hope you appreciate it. Guys, this is my second video on this channel and maybe my third video I've ever made ever. So if you guys have any sort of feedback or anything that you would like to tell me, like something, I know I put some images in here. I don't know if I actually ever got into doing the animations while I'm recording this, but if you don't like the way that if the explanation doesn't make sense, or you feel like the explanation is wrong, if you'd like for me to talk about something else, if you think there's something weird about the video itself, the audio, the graphics, the words, any of that stuff, please go ahead and let me know in the comments, and I will take that feedback into consideration, because I do want to make good videos. I want to help as much people as I can. And if this video helps even one person who wants to understand this stuff, and not just the people who I make watch this video because I'm trying to get feedback, just one other person, that's all it would take for me. So please go ahead and leave that feedback. And so with all that said, thank you for watching, and adios.